Yeah, I think I should record this. Anyway, thank you. So, right. So this is the so-called syllabus part 2. Okay. And it just gives a lot more detail. And one thing you'll see on here is when it comes to this coming week. So here we just did the wrap up. See, that's the, let's see if I can, so we just did this. Well, some of you haven't done it yet. You'll do it tomorrow. Okay. And then you'll see that we're going to have an exam next week. So I want to point out to the people who haven't submitted their academic integrity statement that I'm not going to mail you the exam until I get that from you. And you know who you are. There's quite a few of you. Please send me. This is listed under early information on Blackboard. I need to get this statement from you before I will mail you the quiz. Oh, sorry, the exam. Now I'm supposed to mail that on February 16th, but it's probably going to be, it could be the 17th, a Wednesday, that I'll get it out. I'm not sure. But that's not really what I wanted to show you. What I wanted to show you was that it says that next week we don't have lab, and it says winter recess. Well, I want to clarify that winter recess is the 18th and the 19th. But since the people don't have lab on the 18th, if we did the lab on the 16th, we would be out of sync. So that's why we don't have lab the 16th or the 18th, but we have class both days next week. So we have Monday and Wednesday class meets. It's just that we don't have lab on Tuesday because there's no lab on Thursday. So I just wanted to clarify that, because some people might think, well, if it's winter recess 16, 18, then we don't have class on Wednesday, but that's not true. We have class all next week. So that's what I wanted to tell you about. All right. What's this doing here? Okay, so, okay, I'm recording. Oh, you're welcome about clarifying that. Yeah. Okay, so just wanted to put that in the notes for people who weren't here, but maybe, so I'd want to clarify. We have lecture on Monday and Wednesday next week, as usual. Lab will not meet next week. Okay. All right. So continuing where we were last week, or 2 days ago. Seems like a long time ago. I had shown you this graph. This is a graph of vapor pressure. So this is P-vape, the vapor pressure above a liquid as a function of temperature. So temperature is on the x-axis. And I talked about how these curves increase, how vapor pressures always increase with temperature. But then we talked about the differences between different liquids and how these 3 curves look really quite different for 3 different liquids. And so here's what we affectionately call ether, ethanol, which is ethyl alcohol, and H2O. Okay, so we have 3 different curves. We saw that these 3 curves crossed 30 degrees at different values of the pressure. So in other words, the vapor pressure above a sample of water, that is only 34. That's a very low pressure of water above a water sample. Ethanol, and you know this because you can tell, because ethanol is the alcohol that's in alcoholic beverages, and you really, like, you put your nose in that glass and it could really get in there, you know. It's much more volatile. It goes into the vapor much more easily In fact, you could see it's 80 torr is the vapor pressure of ethanol. And ether, I do not recommend sticking your head into a container of ether. You would be overwhelmed by the smell, by the vapor of ether, which is more than 600 torr. So you could see that's way up here. And the reason for that is intermolecular forces. So the reason for the dependence of the vapor pressure on temperature, well, no, sorry, the reason for the different vapor pressures at the same temperature for different substances is because of intermolecular forces. And I went through and talked about these three different substances. Water, this is ethanol, which is also ethyl alcohol, and diethyl ether, which we just call ether sometimes. And I talked about how in water, we have many, many sites for hydrogen bonding, which is an intermolecular force between water molecules. Okay, so we have many of these different sites for hydrogen bonding between neighboring molecules. So there's lots of chances of hydrogen bonds forming. Remember, a hydrogen bond is not a real bond. It is an intermolecular force. And you have to have a hydrogen that's covalently bonded to an O NRF that interacts with an O NRF on another molecule. So this is a hydrogen bond right there, that dotted line, okay? This is a covalent bond. That is not a hydrogen bond, okay? Anyway, so there's lots of places for hydrogen bonding from water molecules to other water molecules that keeps them, that makes it difficult for them to break away to the vapor phase. You have to supply energy to break up those attractions. In ethyl alcohol or ethanol, there is one OH. So this can form a hydrogen bond to an OH on another molecule. Okay, and that's a hydrogen bond, but the rest of it has only dispersion forces. So it's not going to have as strong of intermolecular forces of attraction as water. So more of it will be able to get into the vapor. Now we have diethyl ether, which does have a dipole, but it is a weaker intermolecular force. So it's weaker than hydrogen bonds. And even though it has a higher molar mass, so it would have greater dispersion forces, the dispersion forces really can't compete with hydrogen bonds. So it takes less energy to separate ether molecules and put them in the vapor phase. They go there more easily. So this is where I ended the last class. And this explains why water has the lowest vapor pressure and ether the highest for these three liquids. Okay. And I guess I was going to write all that stuff there, but I didn't. And I encourage you to look at the video. There is a video, and it's called something like Understanding Liquid Properties from Structure. And it just does more of examples and talks about it more. In fact, it talks about lots of different properties. There's also a video on surface tension, which we are not going to talk about during lecture, but you need to know about it, and viscosity that are discussed in another video. Okay. All right. So now I wanted to talk a little more about these three liquids. And what else can we figure out from this graph? Okay, so here's the graph. I put it up again. Oh, I know what. So if you have a lower vapor pressure at a given temperature, and we know what the boiling point is. So boiling point Boiling point. Does anybody remember what the boiling point is? It's the temperature when what happens? Don't say it's the temperature when the liquid boils. While that is true, it forms the big bubbles at the boiling point. That is not the definition of the boiling point. It's the temperature when what?
When the liquid reaches atmosphere.
Sorry, you got all washed out at the end of your sentence.
When the liquid reaches atmospheric pressure.
It's not when the liquid reaches atmospheric pressure. It's when the vapor, right? You're right, above the liquid, right? Reaches atmospheric pressure. So we live in Rhode Island. We live at sea level. The atmospheric pressure is 1 atmosphere. So it's the vapor, it's the temperature when the vapor pressure is so high that it actually equals atmospheric pressure. How do you know this happens? Is you get these very large bubbles. Bubbles start to form in the liquid, but they don't break because their pressure is high. So that you end up with these large bubbles that don't collapse because they have a pressure that's equal to the atmospheric pressure, even inside the bubble. And that's why you get that bubbling action. Okay, so on this diagram, you can easily see where the vapor pressure equals atmospheric pressure, at least at sea level. It is this red line here. This line represents 760 millimeters of mercury, or 760 torr, or 1 atmosphere. So where each of these lines crosses that line, that's the boiling point of each liquid. So this one you can see is about 35 degrees C for ether, about 78 degrees C for ethanol. And of course, we know it's at 100 degrees C for water. Okay, so it's where the vapor pressure keeps increasing and increasing. And then at this point is where it equals atmospheric pressure. That is the boiling point. So these are the 3 boiling points of these 3 liquids at sea level. Okay. So the question is, why is water's boiling point so much higher than ethanol's and diethyl ether? And it's really the same bunch of information that we just used when we were talking about why the vapor pressure of water is lower and the vapor pressure of ether is higher. Okay, so to get to the boiling point, you have to have a high vapor pressure. You have to have vapor pressure equal to atmospheric pressure. The greater the intermolecular forces, the more energy is needed to go into the vapor phase. The more energy is needed to break away from your neighbors, okay? That means you need a higher temperature to get the vapor pressure to equal the atmospheric pressure. And this leads to a higher boiling point. So greater intermolecular forces, higher boiling point, and of course that would have a lower vapor pressure at just about any temperature than something with weaker intermolecular forces. So this something with greater more energy needed to get into the vapor phase. So P vape tends to be low, greater intermolecular forces, low vapor pressure, higher boiling point. And so water has the greatest intermolecular forces of these 3 compounds. It has the lowest P vape, vapor pressure at any temperature, and it has the greatest BP. And ether would be the opposite. It has the smallest intermolecular forces. It has the highest vapor pressure at any temperature, and it has the lowest boiling point. So you could see already how boiling point and vapor pressure, two properties that are like fundamental properties that liquids have, how they vary with intermolecular forces. Liquid properties are very closely connected to intermolecular forces. Okay, so here's activity 2. I didn't do this yet. Here's the same graph. This is really just another version of the same graph. And basically you're asked here to estimate the boiling points for these 3 liquids at sea level. And at sea level, the atmospheric pressure is 760. Well, we just did this, right? These are the 3 points. These are the same 3 liquids. And so we just got through. You could see here that this dot here, the temperature is about 35 degrees C. If you bring this down here, it's about 80. The other graph was a little more precise, so it gave you more precise numbers. And you could see this is 100 degrees C. So we really did this already. But what we didn't do is say, well, what if we were at a high altitude, okay? For example, if you're in the lab in Colorado, where I did a postdoc for a while, and the atmospheric pressure is lower. Now, it's not 600, okay? It's a lot, it's not that low. But just for the purposes of using this graph easily, since there's a grid line here at 600, let's say we were, well, I'm sure there is a place where well, I'm not sure, but I think maybe higher than where I lived, at some altitude on a mountain in the world somewhere, there is a atmospheric pressure that's about 600, and we're going to figure out what the boiling points of these liquids would be there. Okay, so what would the boiling point of water be? Well, you could see that if you take this crossing point here and bring it down to the x-axis, it looks like it's in the 90s. Maybe it's like, this would be 90, so maybe it's like 93 for water. Yeah, if I put this on a test, I wouldn't expect you to be perfectly precise. I'd give you a range of values I would accept. What about for ethyl alcohol? It would be maybe, I don't know, like 72-ish. What do you think it would be for ether? So now this one here, we bring it down. What do you think? Actually, I think I may have. I think I moved the line a little. Probably is more like over here. I don't know. It looks like about 30 degrees. You see what I'm doing here?
Yeah.
Okay. Good. And just to be able to interpret this graph, what is the approximate vapor pressure of ethanol and of water at 40 degrees C? So see what you think about that based on this graph. Ethanol at 40 degrees C. So this is the ethanol graph here. 40 degrees C, it's about there. Maybe it's 150. So it'd be 100, maybe 120, 30, something like that. Let's call it 140. You see what I'm doing here?
Yeah.
And water, now water at 40 degrees about here, right? So that would be, I don't know, maybe
70?
What'd you say?
70?
Yeah, I think so. Out like that. Out 70. Okay, so from one of these vapor pressure graphs, you can estimate boiling points at different altitudes, at different pressures. And so it's a pretty cool thing to know. I did already warn you, if you were going to do some high altitude cooking, that the boiling point is lower, right? So if you're somewhere where you're cooking your rice, say you're boiling rice, and it's, 93 degrees C is the boiling point at 600 millimeters of mercury. So that means you're cooking your rice at 7 degrees cooler temperature. So it would take longer. And you end up with more evaporation of water. And so you have to add more water. There's all kinds of cooking hints online about baking and making different things. But the first time I tried to make rice, it was kind of hard and it was pretty yucky. So I had to add more water and cook it longer. But anyway, it didn't come out that good even when I did that. But I learned eventually. It was a little bit better. Another property I want to add. So we've talked about vapor pressure. We've talked about boiling point. But there's a very closely related property that I want to make sure you know about. And that's the heat of vaporization, which is called the delta H vape. And this is, so if I wrote the process, here's liquid going to gas. Okay, and remember back in first semester, you put a little semicolon here and you put the enthalpy change for this process. I've been saying 40, but it's really 41 kilojoules per mole. And this is called the heat of vaporization for 1 mole, right? Because this little guy here means it's a standard enthalpy change, and it means for 1 mole. So the energy needed to vaporize something is extremely closely related to those intermolecular forces. If you have stronger intermolecular forces, that means it requires more energy to pull molecules away from each other. And that means that's exactly what it means to have a higher delta H of vaporization, because the heat of vaporization is the energy needed to do this for 1 mole. Okay, so there's a open and shut case. Stronger intermolecular forces, more energy needed to separate molecules, greater heat of vaporization, because that is what that energy is. Okay, now I also want to talk about some other closely related properties, because remember, this chapter is not just on, or unit, it's not just on liquids, it's also on solids. So there's some solid properties that are very closely related to this as well. So let's see. So don't forget, it's, when you go from liquid to solid, there are the same molecules in the solid as in the liquid. So there's really the same intermolecular forces, but they may be closer or further apart. So maybe they're not exactly the same strength, but the same types of things can happen. All right. So if we're going from water in the
Can you go a little bit up, please?
Sorry?
Can you go a little bit up? Yeah, okay. Yeah, thank you. Thank you, that's it.
Okay. So you know how I just drew water liquid going to water gas? Well, I could talk about water solid going to water liquid. And this also has an enthalpy change. This also requires heat. This requires heat. So this delta H is positive. Remember that when you have something that requires heat, it's an endothermic process, the delta H is positive. So the delta H for this process, okay, is actually also positive. So you notice it requires energy to go from solid to liquid, just like it requires energy to go from liquid to gas, but it requires less energy. And that makes sense, right? Because when you're breaking those hydrogen bonds, say from water, you're not actually moving them all that far away when you're going to the liquid. When you're going to the gas, you're really pulling molecules way far apart. So it requires more energy. So this number is considerably smaller than the heat of vaporization. But this has a name too. Does anybody know what this is called? Because it's a very funny name. It doesn't, what is this process? This is melting. But we don't call the delta H the heat of melting. We call it something else. Does anybody know what it's called? It's weird. The heat of fusion. I really wish they would change that name because it's very unintuitive for students. But I would like to say that if something has stronger intermolecular forces, it will have a greater heat of fusion or enthalpy of fusion. It will require more energy to go from solid to liquid, just like it requires more energy to go from liquid to solid. Okay. And so, for example, if I took ethanol, which I'll abbreviate as ETOH, right? So that is ethanol. If I go from the solid to liquid ethanol, oops, you can't go from ethanol to water. So we're melting ethanol, which would happen at a different temperature than the melting of water, but that's okay. This delta H of fusion, well, these are weaker intermolecular forces. There's hydrogen bonds, but there's many fewer of them, and there's weaker dispersion forces. So overall, you have weaker intermolecular forces in ethanol. So those molecules are not held together as strongly. And the heat of fusion is smaller. It's actually 4.60 kilojoules per mole. So this is a smaller delta H0 of fusion. Okay, so this has weaker intermolecular forces, and so it has a lower delta H of fusion. Okay. What else? If I'm talking about melting, and I've talked about boiling point, what about melting point? Okay, so what happens when you melt is you pull apart molecules in the solid, and then they're a little further apart, usually, and they're in the liquid. So melting point depends on intermolecular forces as well. So compounds that melt, that need a higher temperature to melt, are compounds that have stronger intermolecular forces because they need to have more input of heat, a greater temperature in order to melt. So the greater the intermolecular forces, the more energy required to melt a solid, and the higher the melting point. Okay, so we've covered 3 properties of liquids: vapor pressure, boiling point, heat of vaporization, and 2 properties of solids: melting point and heat of fusion. And all of those, well, vapor pressure excluded, right? Vapor pressure stays low when you have strong intermolecular forces. All those other ones go up with increasing intermolecular forces. And it's all written down in these notes. Okay, so I want to take a look at a few simple molecules. These are diatomic molecules. This is activity 3. And so I've just listed for you a series of diatomic molecules. These are H2, F2, Cl2, Br2, and I2. So where are they on the periodic table? Well, the periodic table, we have hydrogen over here, right? Our first column, and then, I don't know, I'm not drawing a very good periodic table. But hydrogen is over here, and the others are all over here in columns in group 7. Okay, so this would be H2, and then Cl is over there. So F2, Cl2, Br2, I2. That's where they are on the periodic table, just so you can get acclimated to them. Okay, and I've given you boiling points here. Now these are in Kelvin. All right, so 20 Kelvin is not that far above absolute zero, right? And then it keeps increasing as I, in that order from H2 to I2. So the first thing I wanted to think about is, can we tell, and we can, by looking at these boiling points, which of these are gases at room temperature and which are haven't turned to the gas phase yet? Okay, so what I want to do is talk about that. So first of all, what is room temperature? Anybody know what room temperature is? 25 degrees C, we call it room temperature. It's 70, around 69, 70 Fahrenheit. It's 298 Kelvin, right? That's what we call RT around here, room temperature. So the question is, which of these are gases at room temperature and which of these are liquids? So the boiling point of a liquid, oh, well, let's say yes, is the dividing line. And what I mean by that is that below the boiling point, okay, the stable phase of a liquid. So it's under the boiling point. What's the stable phase? I shouldn't say of a liquid, of a substance. Let's call this a substance, right? The boiling point of a substance divides from below the boiling point, where the liquid is the stable phase. Stable phase of a substance is a liquid below the boiling point, to above the boiling point, the stable phase is the gas. You know this. If you measure the temperature of boiling water, it's actually 100 degrees C. Okay, and once all that water gets converted over into the gas, now you have steam, and the temperature goes way up above 100. I'm going to talk about this later on in class. But that's why it's so bad to get a steam burn, because those burns can go way up higher than 100 degrees. But the boiling point is the dividing line. So below the boiling point, the liquid is the stable phase. Above the boiling point, the gas is the stable phase. So for example, if we have H2O, that's the substance that we're most familiar with. So below the boiling point, so below 100 degrees C, it's a liquid. So water at 80 degrees C, for example, would be a liquid. That's the stable phase. Above the boiling point, so above 100 degrees C, the gas is the stable phase. So if you had water at 150 degrees C, or 155 degrees C, that would be a gas. Okay, at 100 degrees, you've got both of them. So anyway, if you take a look at the diagram, at the chart that I just showed you, it has boiling points. So the question is that boiling point above or below room temperature? So we have to put room temperature here. And room temperature is 298. So all the substances that have a boiling point, these guys have a boiling point below room temperature, what are these at, what is their phase at room temperatures? At room temperature? Are they liquids, are they solids, or are they gases? Well, they boiled already below room temperature, right? So this guy boils at 20 degrees. So at 20 degrees Kelvin, it's already a gas. That's its stable phase, above 20. Here, above 85 Kelvin, above 85, it's going to be a gas. And here, above 238, it's boiled already. So that's because their boiling point is below room temperature. These are gases at room temperature. And these are solids or liquids at room temperature. And in fact, for bromine, it's a liquid at room temperature. And for iodine, it's a solid at room temperature. And that's because its boiling points, the boiling points are above room temperature, all right? So that's what we can tell by looking at this. So let's take a look at these 5 diatomic gases. There's 2 atoms, that's why we call them diatomic. And so I just want to talk about why do the boiling points increase as you go in this direction from H2 to I2. So I just want to review a couple of points. These are points we made already that I've talked about. Boiling requires getting liquid molecules to go into the gas phase. This means separating molecules from each other, all right? Remember, it requires getting liquid molecules to go into the gas phase. Remember, because the vapor pressure has to equal atmospheric pressure. So to get to the boiling point, you have to have all those molecules of gas above the liquid, and that pressure has to equal atmospheric pressure. That means you have to separate molecules from each other. So the stronger the intermolecular forces, the more energy that's needed for that process, and the greater the boiling point. That's a fact about boiling point. Now, to answer this question, to figure out why the boiling points increase like this, we have to talk about the intermolecular forces in each of these and how they change. Okay, so let's talk about intermolecular forces. So we have H2. I'm just going to draw H2 and say Cl2. All of them look the same. They just have different letters there, right? Is there a dipole in any of these molecules?
No.
That's right. No dipoles. Why are there no dipoles? Because you have 2 of the same atom. So there is 0 difference in electronegativity because it's the same atom. There's no dipole, okay? So there's no H bonded to an O, N, or F, so there's no hydrogen bonding, okay? So with that, what is the only type of intermolecular forces that can be present here? What's it called, that other force? The only force that exists between nonpolar molecules is called, yes, dispersion. And in fact, I can save myself the energy of writing that because it's the same. It's exactly the same. They all have dispersion forces only. So now it's asking you to rank the strength. So are all these forces equally strong? It's right. It's only dispersion. And are they equally strong in all these molecules, the dispersion forces? What do dispersion forces depend on?
No.
That's right. The answer to that is no. And why is that? What's different about them? These have different sizes, right? You have H2, F2, Cl2, Br2, pretty boring. Okay,
Molar mass.
sorry,
Molar mass.
I didn't hear you.
The sizes are different and so is the mass.
They have different masses, yes. They have different masses. They're different. Remember, look at the spots on the periodic table. I think I drew a little picture of it right here, see? So as you go down from hydrogen to fluorine, you go this way, the size increases. The size meaning the number of electrons. But, and this is, you could tell this because the molar mass increases. And remember that the larger the electron cloud, okay, the larger the electron cloud, the greater the ability to distort that electron cloud. So as you go from H2 to I2, the size of the electron cloud increases. Okay, and also you could see that because the molar mass increases. So this goes along with increasing molar mass. Okay, and this means greater dispersion forces. So let's rank them. This would be the strongest dispersion forces. This is the largest, heaviest. And this would be a 1. So it's just 2, 3, 4, and 5. So bromine, iodine, I2, has the strongest dispersion forces among these molecules. Hydrogen has the weakest. So you have greater intermolecular forces going this way. Greater dispersion forces. So do the observed boiling points make sense? What do you think?
Yes, because it requires more energy to break apart the heavier atoms. I mean, heavier, you know what I'm talking about.
Yeah, it requires more energy to pull apart two iodine molecules from each other. Notice how specific I am with my language there. I train myself to talk this way rather than say to pull two iodines away from each other, because then you might think I'm talking about breaking the bond. I'm very careful with language here. Yes, it makes sense because it requires more energy to pull apart two iodine molecules from each other than the energy required to do the same, or to do that for H2 molecules. This is because I2 has stronger dispersion forces than H2, and everything in between, right? Because it increases as you go, H2, F2, Cl2, Br2, I2. Okay, and in order to boil, the vapor pressure has to equal atmospheric pressure. So I2 will need a greater temperature for P vapor to equal P atmosphere. It needs more energy to get to that point. Okay. Does anyone have a question about that example?
Does it say in order to block or break?
Break. Where is that?
Right after I2 has stronger dispersion forces than H2 in order to boil. Is it boil?
It says boil. Yeah, boil. Boil. The vapor pressure has to equal atmospheric pressure. So iodine will need a greater temperature. Somebody asked a question, maybe. But because there are two adjacent atoms occupied. Oh yeah, okay, fine. I don't think I need to address that. Yes, these are two atoms, each are the same. So get those temporary dipoles, that's what dispersion forces are. Okay, so that's a pretty simple example, all right? Let's go a step up in difficulty. Let's take a look at this for activity 4 now, okay? So now we're comparing some other gases, HCl, HBr. Well, these weren't all gases at room temperature, but these are all gases at room temperature. In fact, the temperatures, the boiling temperatures, these are the boiling points. These are actually given in degrees C. I know this is a little small, but so you could see these are is negative 84.8 for HCl. And you could see for HI negative 35.1. All of these guys have boiled before room temperature, because room temperature is 25 degrees C. So these are all gases at room temperature, but they're not identical. They have different boiling points. They don't all boil at the same temperature. The question is why? So we have a couple of different things here, right? These are not quite as simple as the example I gave you before. So if we look at HCl, right, we have a dipole there. So this, and in fact, it's the example I gave you of a dipole force back when we talked about it. So this is a DD force. Okay. And it turns out that the dipoles vary in these diatomics. And this column here, I haven't told you about a dipole moment. I'll just write this a little darker. But this is a dipole. The dipole moment tells you the strength of the dipole. Now, this has to do with a couple of things. Mostly it has to do with the difference in electronegativity, which is what we've been using all along to judge, how strong a dipole is. But also it has to do with the distance apart. I just want you to look at this number here and view it as the strength of the dipole, okay? So don't try to overanalyze it. It's just a piece of information that tells you how big that arrow is. And actually for HI anyway, if you looked at the electronegativity difference, it's actually only 0.4. So by the freshman chemistry gauge of whether there's even a dipole, we would say that that was nonpolar. And this very small number indicates that, well, maybe freshman chemistry doesn't explain all of chemistry. So we just acknowledge that there is a tiny dipole there, but you can see it's just a smaller number than the others. So I have dipoles listed here, and I also have molar mass, but I kind of made a mistake here, and I didn't add in the mass of the hydrogen. So really the molar masses are 36, 82, and 129. Sorry about that. But anyway, you could see most of the molar mass is not from the hydrogen. Okay, so first of all, let's think about the intermolecular forces here in these different diatomics. All right. Now, what I've also put here is the molar mass. So we'll have it all together and the dipole moment. So is there any hydrogen bonding in any of these three? We have HCl, HBr, and HI. Is there any hydrogen bonding? What do you need the hydrogen to be bonded to get? Yes, somebody said no. Good. There is no O, N, or F. So the answer is no. So no hydrogen bonding for any of these. Is there a dipole-dipole force? Okay. Well, I gave you dipoles. So here in HCl, that was the largest number. So I'm going to say that has the largest dipole. They all three did this, had the smallest one, HI, very tiny dipole. So what intermolecular force? Oh, what about dispersion? Well, you always have dispersion forces. So I can put yes in each one of these. Okay. So now it's asking, based on the molar masses, what happens to the strength or the magnitude of the dispersion forces as you go from HCl to from HCl to HBr to HI. So what you see is you have an increasing molar mass as you go down. So what's going to happen to the, what do I put in here? What happens to the magnitude of the dispersion forces as the molar mass increases?
It increases.
Yes, that's right. So I guess I would say this has the greatest, because it has the greatest molar mass, and this has smallest dispersion forces. Okay, what about the dipole-dipole? So based on the dipole moments, which has the strongest and which has the weakest dipole-dipole? Well, that's going to depend on this column, right? So the strongest dipole-dipole force will be between two molecules that have the strongest dipole. So that would be HCl, right? That would be the strongest. And then the weakest would be HI. And then middle would be HBr. Okay. All right, so which of these substances actually has the lowest boiling point? And here is where you have to tell yourself the boiling point actually tells you the truth about the strength of intermolecular forces. If something has a lower boiling point, that means that it has weaker intermolecular forces. So I want to write that down. I want to say that the boiling point tells the truth about which, or the boiling points tell the truth about which substance has the strongest and weakest intermolecular forces. So if you look at the boiling point chart, it tells you HI has the lowest boiling point. HCl has the highest. Oh, sorry, I have that backwards because these are negative numbers. So HI has the highest boiling point and HCl has the lowest. All right. So that means since HCl has the lowest boiling point and the highest is HI, which of these has the greatest and which has the lowest intermolecular forces? the one with the lowest boiling point, okay, has what? The weakest or the strongest intermolecular forces?
Weaker.
Okay, so let's look at this, okay? The weakest intermolecular forces is HCl. The strongest would be HI. So what does that mean in the case of these three molecules? What type of force appears to be the most important here in determining the boiling point, determining intermolecular force strength? Is it dipole-dipole or dispersion? You have to think about this because this is a little complicated, right? The boiling points tell us that HCl has the weakest intermolecular forces. So the boiling point tells us HCl has the weakest intermolecular forces because it has the lowest boiling point. But HCl has the strongest dipole. Okay, so let me just write the boiling points here. So this is the highest boiling point, and it goes with the greatest dispersion forces and the weakest dipole. Do you see that? So we're kind of taught that dispersion forces are the weakest forces. But does that appear to be the case here? Dispersion forces increase this way as boiling point increases. So the boiling point is determined in this case not by the dipole. If it was dipole forces that were being more important, then HCl would not have the lowest boiling point. It would have the higher boiling point. So this simple example is not that simple, and that's why I'm showing it to you. So I guess in the case of these three molecules, dispersion forces are the most important. And it says, are you surprised by this? And how can you explain it? So I guess I would say that we are taught that hydrogen bonding is the strongest intermolecular force, then dipole-dipole, then dispersion. So this is a surprising result. And the reason it's surprising is because HCl has the strongest dipole-dipole force, and yet it is not the highest boiling. It's the lowest boiling. But here, clearly, dispersion forces kind of rule the day. So why do you think, as you're going from HCl to HBr to HI, why are dispersion forces so important? And dipole-dipole forces don't seem to matter that much in terms of the boiling point. You know, why do you think that is? And I think that what we need to think about Delon, I don't want you to get to say anything generally about how, just usually greater dipoles, everything else being constant. Like if you had 3 different compounds that had different dipole forces, but the same dispersion forces, then there would be no doubt that the one with the greater dipole would have a higher boiling point. Okay. But in this case, when we look at what's happening to the molar mass, okay, so we have to look at these numbers, 36, 81, 82, 129. So there's a huge increase in molar mass. And so there's a huge increase in dispersion forces. So even though the dipole is going down, right? Even though the dipole force, I guess I could say, gets weaker as you go from HCl to HI, okay, the dispersion, the great increase in dispersion forces must more than make up for it. And the way I know that it more than makes up for it is because the boiling point tells me the truth, right? The boiling point tells me that HI has the greatest intermolecular forces. So, so I just want to say, this is a bit of a little, this is an example that tells you that general statements can be somewhat misleading. Like I say, okay, dispersion forces are generally weaker than dipole. But in this example, the great change in dispersion forces because of the great change in molar mass, that makes all the difference. And it's the reason why HI is higher boiling than HCl, despite a lower dipole in HI. So anyway, so I want to tell you that science is full of fine points like these, especially when you try to, relate a property like boiling point to structure. There's a lot of different things to think about. But, in general, if you compare 2 molecules that have the same dispersion forces, the greater dipole force one will have a greater boiling point. If one of them can hydrogen bond, it would have the greater boiling point, which brings me to my next molecule. So that kind of segues very nicely into the next one. So here, if I tell you that the boiling point of HF is 19.7 degrees C. So let me actually make a chart of HCl, HBr. This is what I already showed you, these boiling points. And HI, their boiling points we've already discussed, minus 84.8 degrees C, minus 66.5, minus 35.1. But now I'm adding HF to this chart. And its boiling point is 19.7. So what do you think about this? So we've already talked about, as you go from HCl to HBr to HI, we have the dipole decreases, and yet the boiling point increases. And what do we attribute this to? This is attributed to the great increase in molar mass. And so greater dispersion, much greater dispersion forces. It's very easy when you have the boiling points to say, oh, this one has greater intermolecular forces than that one. Okay. So once I have the boiling points, I can make a rationalization here. And it seems that definitely it's due to the increase in molar mass. But what about HF? You know, why did that happen suddenly? Wait a minute. Hello? Hello? Right, suddenly I'm getting a terrible echo. I have no idea why. I don't know why it changed.
You have two mics on.
Oh, and maybe I got that mic on by mistake. Yeah, I must have hit something in that. Yeah, thank you. You're right. Good. All right. So if we go back to the molar mass, we had 36, we had 79, and 128. What's the molar mass of HF? It's something like 20 grams per mole. So it says, what if I tell you now that the boiling point of HF is 19.7? How can you explain this? The boiling point of HF is 19.7. That's the highest of all. And yet it has this tiny molar mass. So what's the reason for that? Somebody said, would this be connection of the ONF? Yes. HF can form hydrogen bonds with neighboring HFs. And hydrogen bonding is the strongest intermolecular force of all. So despite its very small molar mass, HF is the highest boiling of these. HF molecules, you need the most energy to pull them apart of all of this, in the ones in this series. And, you know, HF, well, got a hydrogen bond. Okay, it's the dotted line, that's the hydrogen bond. Okay, all right. So that's why. It's kind of an interesting series of very simple molecules. All right, so I want to encourage you again that there are those two videos for you to watch that'll give you more and more on liquid and intermolecular forces. And I told you what those names were, and they're posted. And if you go to Unit 2, it has the links for them, although it's in the place where you find the lecture videos on YouTube. And so what I want to do is just assign this. So I'll talk about it a little bit, but this is going to be your next graded assignment. And there's actually 3 activities together on one page of the activity sheet. This one I think you could do right now, except for maybe the surface tension one, which you have to watch the video. But we talked about this today. This one, activity 7, addresses the difference between methanol. So methanol actually looks like this. It's CH3OH. So it's got 3 H's. It's in a tetrahedral structure like that. And methane is also a tetrahedron, but it doesn't have that OH. Okay, so I'm asking you to compare these 2 molecules. Which would you expect to have the greater heat of vaporization, and why? So you need to compare the intermolecular forces in these two, which are greater. So the first thing is which has greater intermolecular forces and why. So describe them. And then you want to relate intermolecular forces to heat of vaporization. Okay, and you want to answer that question. Hydrogen bonding is part of the answer here, and I want you to show how methanol molecules form hydrogen bonds with other ones by basically drawing two structures and the hydrogen bond between them. And then there's activity 8 here. Okay, now this one's a little more complicated, but it's not, it's not more than what you can handle. So I would like you to rank these compounds in order of increasing boiling point, okay? And explain. The most important thing, I mean, everybody in this room, these many rooms, can look up the boiling points of these compounds. That's not what this exercise is about, okay? This exercise is really about explaining it, okay? So not just give me the order, but explain it. So what you need to do is, first of all, you need to calculate the molar mass for each one of these to compare dispersion forces. And I want to tell you that a lot of times students want to attribute a large difference in intermolecular force when there's like a difference of 2 grams per mole in molar mass. And I just want to say that differences of 2 or 3, grams per mole are not significant. So you'd have to have a greater difference in molar masses than that to say that the dispersion forces were a lot different. You need to talk about the types of intermolecular forces for each one. Okay, so you can look at them. Don't forget this is an OH here. So there's don't forget that. Of course, are there dispersion forces, dipole? Is there hydrogen bonding? And the best answers will compare the intermolecular forces and use that to explain the order of the strength, of the order of the, would compare the intermolecular forces, will explain what boiling point is. And then we'll link the order of the intermolecular forces to the boiling point order. Okay. And it should also even explain why increased intermolecular forces means a greater boiling point. That's part of the answer. That will be part of the best answer. Okay, so there's all different kinds of answers you can give, but you want to say, compare the intermolecular forces, talk about why increased intermolecular forces means, greater boiling point. What's a boiling point, and what is that, and what do intermolecular forces even have to do with boiling point? And then to give the order. So that's going to be graded assignment 2 to do these 3 activities. And that's going to be due Monday. And you have to see Blackboard. What day is Monday? February 15th. Okay. Any questions about that? All right. Okay. Well, I have some more stuff I would like to tell you about water, and also about phase changes in general. So I had said that I would come back to phase changes, and I'm going to do that. So a little more on phase changes. Phase changes means, solid to liquid liquid to gas. That's what I'm talking about. So I talked about today that if you go from solid to liquid, it requires heat. If you go from liquid to gas, it also requires heat. And that means there has to be an input of energy. So we know some things already. We know what the delta H of fusion, and we know the delta H of vaporization. We know these are both positive because that's what that means, because they all require heat. But what I'd like to talk about next is what happens when you heat a sample of water. And in particular, what happens to the temperature? Because it seems quite obvious. It seems obvious the temperature is going to go up when you heat a sample of water, and it does. But my question is, does the temperature increase continuously? And, this is probably something you've seen before in other classes. And we refer to, so we're going to look at a curve. Basically, what it is we have temperature on the y-axis, and we have added heat over here on the x-axis. So we start out with water frozen as ice at negative 25 degrees C. Right? Negative 25 degrees C, solid ice. But as we add heat, and we're good, and if heat is added at an even pace, incrementally, what happens to the temperature of water? Does it go up continuously or not? This is called the heating curve for water. And if it just went up continuously, that would be pretty boring, and I probably wouldn't even tell you about it. But that's not what happens. So here is a crazy diagram. So let me first show you that what the different numbers refer to. So number 1 is referring to solid ice. So you can see here you have a very rigid structure. I'm going to talk about the structure of ice next time. Then what happens is you have ice melting. And so here you see some of these rigid structures, but you have also some separated water molecules. So you have both solid and liquid. So here you have solid only. As you continue to heat, you'll end up getting all liquid. And then you'll get, of course, some gas phase molecules above the liquid. And finally, here you have all gas. So that's what we're looking at, is what's happening to the different phases as we heat a sample of liquid water. So number 1 refers to solid water. And where this diagram starts is at negative 25 degrees C, right there. And it's and the water is ice, all ice there. Okay, so the first part of this curve I want to look at is going right here. As you heat that ice, you can see that temperature here is on the y-axis. The temperature increases. So as the ice heats, the temperature increases. Okay, and then something happens over here. And what happens there, that's 0 degrees C. What do we know that 0 degrees C is? What do we call that? What happens to ice at 0 degrees C?
Freezes.
Sorry?
It freezes.
Well, actually, but we started out freezing, so it'll melt. So we're going the other way, right? So it's the, right. Actually, the melting point is the same as the freezing point. It's just that when you're going down in temperature, we call it the freezing point. When we're going up in temperature, we call it the melting point. It's the same thing. It's the same temperature. So remember that heat is being added. That's what this axis is here. It's representing the addition of heat. But that heat is being added at a constant pace. All right. But what happens at this part in the diagram, you've heat increased the temperature from negative 25 to 0. But now, as you continue to heat, you're still adding heat, but the temperature isn't going up anymore. Okay. So what's happening here, and this I would call this number 2, right? Now the ice is melting. So whereas before all the heat was going into the kinetic energy, moving those molecules, now the heat is going into melting the solid. So the heat added serves to melt the solid. And until all the solid is melted, there is no change in temperature. No change in temperature until all of the solid melts. And then you could see over here, now the temperature starts to go up. So what has happened there is now we are in region 3. And region 3 is liquid water. So all of the ice has been converted to liquid, and now I'm heating liquid. And as you heat the liquid, the temperature goes up. So you continue to heat, but now you're heating liquid, the temperature rises. Okay. Until you get to here. And that is 100 degrees C. That's the boiling point. At this point, as you continue to heat, change my color. I'm trying to change colors. Continue to heat, but there's no rise in temperature. Oh, sorry. Yeah, that's right. Until all the liquid gets converted to gas. There. When all the liquid gets converted to gas, and then the next thing that happens, now the gas heats up. And let me tell you that this curve goes up very fast. The gas heats up, and it can go up and up and up. Which is why you really worry, like you make popcorn in the microwave, and any water that's in that bag has been converted to steam. And now the continuous pumping with the microwaves serves to increase the temperature of that gaseous water, which is called steam. And this is why you have to worry about steam burns. As the water that's now vaporized heats up still more. So what we have in this graph, it's a crazy graph, is we have these different regions. So, it looks kind of like this, right? It goes up and then flat and then up and then flat and then up, okay? From the beginning of the graph. Okay, and this is what I call the heating curve for water. And so we had these different regions. Let's see, we had region 1 and region 3 and region 5. And those are regions where the temperature is rising, right? As you continue to add heat. And then we had the flat regions, right? Region 4 and region 2. So these are flat. Okay. So if we deal with these, you know, if we deal with 1, 3, and 5, these are the regions on the graph. And I would say that there's 2 types. And this is like my first bullet point here, 1, 3, and 5. As heat is added in these regions, and this is when you have solid, liquid, and gas, okay? As heat is added to solid, liquid, or gas, the temperature increases steadily. Okay, there's no phase change here. This is just increasing it's just increasing the temperature of the solid, the liquid, or gas. And you can calculate the heat transferred. We call that Q, okay? And Q depends on how much is being heated up. That means the mass. It also depends on something I'm going to talk about next, called the heat capacity or the specific heat, or it's often called the specific heat capacity. Okay, and then there's the change in temperature. So all of these things, this, by the way, always a change, we call it the final minus the initial. So if you wanted to calculate the amount of heat transferred, you would have to know what the mass of the substance is, what its specific heat is, and how much the temperature changed. Okay. And another thing is if the final temperature is greater than the initial temperature, which it is if you're heating it, right, then delta T is positive, and all of these other things, the mass and CS, are always positive. So that would mean that the heat would be positive. So that would mean that heat is absorbed by the substance to increase its temperature. And of course, if we have the opposite, if TF minus TI is negative, so that means it's being cooled, then Q will be negative and heat is released by the substance as it cools. So there are 2 different things that can happen depending on whether you're going on this graph from right to left or left to right in these regions. And I'm talking about the regions where we have an increase here, right? As a temperature increases with heat. That's what these 3 regions refer to. Okay. So that's how we could calculate the heat there. But then we have another important type of region. That's my second bullet point, okay? And that is heating when the temperature is flat and doesn't change. Okay, so this was 2 and 4, where we had the phase changes. And so here, the heat goes into changing the phase. And we had solid to liquid, so we would be going, if we were talking about water, okay, we know that this requires energy because we know that the heat of fusion is positive, and we know what it is for water, 6.02 kilojoules per mole. Yes, somebody had a great comment, Madison. Yeah, I was going to talk about that. That's great. Yeah. I don't know if I'll get to it today, but I'm not sure. But anyway, So this requires heat. And liquid to gas requires even more heat. I've written this down already once today. Okay. So how would you figure out the heat here? Supposing you have a certain mass of or a certain number of moles of water, and you want to figure out, you know, if I vaporize, say, 2 moles of water, how much energy is that going to require? What is the Q? So the heat that's required or released is the number of moles multiplied by these different values, the delta H 0, either a vaporization or a fusion, depending what process you're talking about. So I just want to say that, so generally these numbers are given in kilojoules per mole. See, these are kilojoules per mole. So you would have to multiply by the number of moles. So if you're given the grams, you would have to convert the grams to moles in order to figure out the amount of heat that transferred here. Okay, so sometimes you're given these numbers in joules per gram, but that's not the normal case. All right, so I'm going to do a little problem for you. Get a little more room here. All right, so suppose I want to calculate, here's an example. So how much heat is required to raise the temperature of 200 grams of liquid water from 0 degrees C, so say it's just melted, it's now liquid, to 55 degrees C. So we're going to use Q equals MCS delta T. All right. And I look up the heat capacity, and it's this circled number in red. Its CS is 4.184. That's, let me write it here. Q is, the mass is 200 grams. This is 4.184 joules per gram degrees C. And now, what is the delta T? So delta T, right, it's 55 minus 0.0. So that goes there. And this comes out to 46,024 joules. So I'm just going, I realize there's only 3 sig figs. So I'm going to call this 46.0 kilojoules, right? I divide by 1,000 to get to kilojoules. So that is the heat that's required to raise the temperature of 200 grams of water by 55 degrees C. That's not really very interesting, but I'm going to compare it to something. Okay, I would like to know, how does this compare? Let me move this a little bit again. Oh, wait a minute. Okay, so my question is, how does this, how about if I rephrase it this way? Suppose I add the same amount of heat to 200 grams of iron instead of water. So I add 46.0 kilojoules of heat to 200 grams of iron. So heat 200 grams of H2O, 46 kilojoules added, versus heat 200 grams of iron. So my question is, this is the question, which would you rather touch? So what do you think the answer to that is?
Water or neither one? I don't know.
It's water. But why? Why is it water? Well, the reason why it's water is because, well, but the thing you have to think about is, what is the final temperature? If you heated the iron. So let's do the calculation. We know Q is mCs delta T. The Q we know because we're going to put 46 kilojoules. So we have 46,000 joules. We know the mass is 200 grams. We need the CS for iron. So I happen to have brought along a handy chart here. And here is the number we need. That is the specific heat capacity of iron. Okay, and now we're going to multiply that by the delta T, which we don't know what that is. That's the only thing we don't know. So we can solve for it by taking 46,000 joules divided by 200 grams divided by 0.450 joules per gram degrees C. And that's going to be the delta T. And the answer is, anybody have any idea? This comes out to 511 degrees C. That is the final temperature of the iron. And that's why you don't want to touch the iron.
I was gonna say that.
So you heat up 200 grams of water and you heat up 200 grams of iron with the same amount of heat. And, you know, I would touch the water way before I would touch that iron. And the reason is because the temperature change is so much higher for the iron. So why is that? And the answer is in this chart here. These are the values of these specific heat capacities. And you could see that H2O, 4.184 joules per gram degree C. This is a really big water has a huge specific heat or heat capacity. Okay. And so irons is much smaller. It's about 10 times smaller. Okay, so you have to ask yourself the question, you know, why does water have such a great heat capacity or specific heat capacity? And that leads to the question, and this is, I think, a fascinating question. What happens when you heat up a substance? So where does the heat go? Okay, so if you put heat in most substances, you add Q into most substances. And what you get, remember we talked about gases. What happens to a gas when you heat it up? You get increased what? Increased kinetic energy, okay? Temperature is a measure of the average kinetic energy of particles. So you get increased kinetic energy, so the temperature goes up, okay? But with water, when you put heat into water, sure, there is some increased kinetic energy and some increase in temperature, but a lot of the heat goes into disturbing those many hydrogen bonds. It goes into pulling water molecules apart from one another. It disturbs the hydrogen bonds. Those hydrogen bonds take in heat and get distorted. So a lot of the heat goes into disrupting, breaking, distorting all those hydrogen bonds. And because water has so many hydrogen bonds, it can really take in a lot of heat without increasing its kinetic energy too much, without increasing the temperature too much. So water can take in lots of heat without increasing the temperature too much because of where the heat goes into disrupting those hydrogen bonds. Yeah. So that affects climate. I'll talk a little. It affects it affects weather. It affects climate. I have a little bit more to say about that, which I'll have to say on Monday. But I just want to remind you to do the graded assignment number 2. I'm working on grading the first one. I'm almost done. And watch the videos. Yeah, because we have an exam coming up, which I'll be giving out probably Wednesday next week for you to do over the weekend until Monday. And that's all. That's all I have to say today. Have a great weekend, a great night.
Thank you.
Yeah.
Have a good weekend.
Thanks for coming.
Thanks. Thank you. Have a good one.
Thank you.
This thing is awful. Ugh. You have a good weekend too. Morgan, I think I got it from you. I'll look on my list if you want to wait a minute. Oh, I don't have it from you, Morgan.